Hi, we continue chapter 7 and it's time now to learn some techniques to calculate the finite expansions. So we already said that if you have a function that is Cn, then to calculate the finite expansion you will use the Taylor expansion. It will be the same thing, and we calculated the finite expansions of some common functions like exponential, sine, cosine, ch, sh, and 1 plus x power alpha and ln of 1 plus x. Now, what if you have a function like sine x, for example, times 1 plus cosine x, something like this, or ln of x, or 1 plus x times sine x, or for example exponential sine x, or sine x plus cosine x. If you have all these examples and you want to calculate the finite expansion, of course you can always say, and this is very important, listen to me very good, you can always say that this function is a Cn function because sine, cosine, ln, exponential, all are Cn functions. And then you can use the Taylor expansion formula. And using the Taylor expansion, you can calculate the first derivative, the second derivative, the third derivative, etc. But if I'm asking for a finite expansion to the order 3, let's say, then you have to calculate 3 derivatives, which might not be very nice because it will take some time to calculate them. You know, to calculate the derivatives, if the function is a little bit complicated, it will take some time. It will take sometimes like forever. So we have to learn some techniques how we can use the formulas that we learned, the formulas about cosine, sine, ch, sh, ln, etc., the formulas that we learned, to combine them in a way to obtain expansions of this kind of functions, for example. So we will not be calculating the Taylor expansion for each one of these. We will not be calculating the derivative of this function for a given order. No, we will be using the expansion we know for sine, the expansion we already know for cosine, and combine them to obtain the expansion of this function, for example. That's what we'll be doing in here. So, of course, the formulas that we learned are valid around 0, so we'll be using them around 0. And if we are somewhere not around 0, around another point, we will make a change of variables to come back to 0 and then to use the formulas around 0. Otherwise, around another point, we don't have any other option than doing the Taylor expansion, the formula as it is. So we start first by the finite expansion of a sum. So if you have a function f of x that has a finite expansion to the order n, and g of x having a finite expansion to the order n, then what about the finite expansion of the sum of f plus g? So the function f plus g will have a finite expansion to the order n if f and g have finite expansions to the order n, and the finite expansion of f plus g will be obtained by adding the finite expansions of f and g separately, each one of them to the order n. So I will take the first finite expansion, the second one, I will add c0 plus d0 to obtain the constant term in the finite expansion of f plus g. I will add c1 plus d1 times x minus x0 to obtain the term of order 1 in the finite expansion of f plus g. Example, if we take sine x plus cosine x to the third order in the neighborhood of 0, so we take the expansion of sine x, which is x minus x3 over factorial 3 plus x3 epsilon x, and then cosine x, which is 1 minus x2 over factorial 2 plus x3. The term x3 has a 0 as coefficient, so it's plus 0 x3 plus x3 epsilon of x. And then we add these two terms, we will have 1 plus x minus x2 over 2 minus x3 over factorial 3 plus x3 epsilon plus x3 epsilon. So it can be written as x3, the first epsilon plus the second epsilon, and this whole thing is something that goes to 0 when x tends to 0, so it's 1 epsilon. So we write plus x3 epsilon of x. Now what if we want to calculate the finite expansion of a product? f times g to the order n. Then the finite expansion of fg will be obtained by multiplying the finite expansions of f and g and by keeping the terms of order less or equal to n. For example, if we take the function exponential x and the function 1 plus sine x, so we know that exponential x can be written as 1 plus x2 plus x3 over 6 plus x3 epsilon of x, and the function sine x can be written as 1 plus x minus x3 over 6 plus x3 epsilon x. Now if we multiply these two expansions, we will have 1 times 1 will give 1, and then 1 times the same one times x will give x, and then 1 times x3 over 6 will give minus x3 over 6, and then you have x times 1 in here will give x times x in here will give x2, and then x times x3 in here will give x4. So the x4, I will write it in here, but it's outside the order that we are looking for, so I will take care of it later. Then I continue. We have x2 over 2, so plus x2 over 2 times 1 plus x2 over 2 times x, it's x3 over 2 plus x5 and so on. And then you have the x3 over 6 in here, multiplied by 1, it will be plus x3 over 6. x3 over 6 times x, it will be x4 and higher order terms. So the terms that have the degree less than 3 are these ones, and this one in here. Okay, so what do I do with the remaining terms and also with the terms x3 epsilon x on both sides? So you have x3 epsilon x times 1 times x times x3 over 6, etc. So what we will do is the following. We will say that all these terms in here and the x3 epsilon x, everybody in here, are terms having a degree higher than 3. So I will put them all together, writing x3 as a common factor times all these terms. But these terms have a degree not only higher than 3, it's strictly higher than 3. So it's x4 and more. So it will be like x times something. So when x tends to 0, all this expression will go to 0. So I will call all this expression the new epsilon x. Okay, so my final expansion in here will be all these terms together. So we have x plus x, which will give the 2x in here, etc. You do the calculation, and then plus the x3 epsilon of x. Now I have a question. If I ask you to calculate the expansion to the order 4, then you should have kept this term of the order 4 and you add it to the expansion to obtain the expansion to the order 4. Is that right? No, that's wrong. Because it's true that if you add this term to the expansion, you are adding a term of order 4, but you are not adding all the terms of order 4. Because if you go back to the expansions in here, okay, you took the expansion to the order 3. The idea is the following. If you want a final expansion to the order 4, it means you should take into consideration all the terms of order 4, not one term of order 4 or two terms, all the terms that are of order 4. And if you take this term, you didn't take all the terms of order 4. To take all the terms of order 4, you should have calculated the expansions in here at the beginning to the order 4. Because if you calculate these expansions to the order 4, the exponential will give a term in here of order 4 that will be multiplied by 1 in here. It will give a term of order 4. So this term we didn't take into consideration. So you cannot use the terms in here to go to the order 4. You should go back to the beginning, do your expansions to the order 4, and then calculate the terms of the product, and then keep all the terms of order 4 or less. Now, what about the composite functions? So if you want to calculate the finite expansion of, let's say, for example, g of f of x, what do? In fact, you will calculate the finite expansion of f and then replace x in the finite expansion of g by the finite expansion of f. But you can only do this if the finite expansion of g that you have is a finite expansion in the neighborhood of a point y0, and the first term, the constant term, the term of order 0 of the finite expansion of f is this y0. I will explain myself. So if f is written as Pn of x minus x0 plus x minus x0 to the power n epsilon x, I will partition the regular part by the constant term, which is f of x0, and the remaining terms that can be factorized according to x minus x0 because they contain all x minus x0. Then if we have the finite expansion of g in the neighborhood of y0, and if f of x0 is equal to y0, then g of f of x is written as g of y0 plus b x minus x0 plus x minus x0 power n epsilon x. So now we have g of all this, right? So if you have this expansion of g in the neighborhood of y0, you can replace y in this expansion by this whole expansion because you are starting by y0. And why is that? Because this is only valid if when y tends to x0, this is tends to g of y0. And here you have g of this package, but this package, when x tends to x0, it goes also to y0. Since it's the case, then you can replace y in here by this package. Let's do an example to understand what's happening. So I will take the first example as exponential sine x. So you can write the expression of sine x, or the finite expansion of sine x. We are doing it here to the order 3. And then you can write also the exponential to the order 3. Okay? You should have both to the same order 3, that is the order that we need to calculate the expansion to. So you have both. Then you can write f1 of x is equal to exponential sine x, and then replace sine by its finite expansion. Until here, it's all good. Now, if you want to go to the next step, where you replace the x in here by all this, because if ex is equal to this, then this package will be equal to the same expression, but by replacing x by this finite expansion of f, or of sine x. If you want to do so, you should be sure that when x tends to 0, this term in here tends to 0, because we are calculating the finite expansion to the order 0. Again, this is true in here, so this is true only if x goes to 0. So if you want to replace x by something, this something should go to 0 as well when x tends to 0. So since this goes to 0 when x tends to 0, then we have the right to replace it. We replace it, and then you have this whole expression. So here what you should do is to expand this expression, but you should only keep the terms of order less or equal to 3, because all the terms that are of order greater or equal to 3 will be grouped together in this x3 epsilon of x, as I explained for the product. So you keep the terms of order less or equal to 3 that will give the expansion in here. So it will be 1 plus x plus x2 plus x3 epsilon x at the end. Now what happens if it's not the case? What happens, for example, if we have e cosine? Because cosine can be written as 1 minus x2 over 2 plus x3 epsilon x. So now, if you replace cosine by its expansion, as in here, you cannot replace the x in this expression by this package, because this package doesn't go to 0 when x tends to 0, it goes to 1. So what you need to do is to make some transformation to change this case. So what we did in here, we wrote this exponential as e1 times e the remaining terms, and then now these terms goes to 0 when x tends to 0, so we can replace the x in here, and then we use the expression of the expansion of exponential, but replacing x by minus x2 over 2 plus x3 epsilon x. So we will have e times all this. We do the expanded form, and then we do the calculation by removing all the terms of order greater or equal to 4, and then they will be grouped into this term in here, and we will have the final expansion, which is e minus e x2 over 2, which means that if you want to calculate f1 at the point 0, it will be equal to e, which is the first constant term of the expansion, and then if you want to calculate f1 prime at the point 0, it will be equal to the constant term, sorry, to the term of order 1 of the expansion, which is in this case 0. Let's take another example. If g of x is equal to ln of 2 plus x, so we know that ln of 1 plus x is equal to x minus x2 over 2 plus x3 over 3. So we take always to the third order because this is what they are asking for. Then h of x is equal to ln 2 plus x. So here also we cannot replace the x in here by the x in here because we have 2. So it's not the same case. So we do some calculations. We write this as ln of 2 times 1 plus x over 2, which is equal to ln of 2 plus ln of 1 plus x over 2. Now we have 1 plus something, and this something goes to 0 as x tends to 0, so we can use this formula replacing x by x over 2. So that's what we do, and you do the calculation to obtain the finite expansion. So in fact, these formulas in here that we did before, we are using them now, but by replacing x by u. So we are doing like sh of u is equal to etc., and u is a function of x that should go to 0 if we are calculating the finite expansion around 0. So it should be going to 0 as x tends to 0. Otherwise, we cannot calculate the expansion of the composite function this way. Another final example, it concerns the function exponential square root of x plus 4 to the second order. So we of course, as I said before, you can take the function h and apply the Taylor expansion, but it will take a lot of time to make the calculation. So what we'll do in here, we'll use the expansions we know. So we know that square root of x plus 4 or x plus 1, sorry, is equal to 1 plus half x minus 1 over 8 x2 plus x2 epsilon of x. And exponential x is equal to 1 plus x2 over 2 plus x3 epsilon of x. So we do both to the second order because this is what they are asking for. And then now we will proceed to do the combination. So square root of x plus 4 can be written as square root of 4 times x over 4 plus 1, which is 2 times square root of 1 plus x over 4. So we can use now this formula to calculate the expansion of square root of x plus 4 by replacing x by x over 4. We do the replacement, and then we obtain finally the finite expansion of radical x plus 4. So we replace now in exponential radical x plus 4, we replace radical x plus 4 by its finite expansion. It will be e to the power 2 plus x over 4 minus 1 over 64 x2 plus x2 epsilon of x. And before replacing the x of this expansion by all this package, we have to be sure that this package goes to 0, but it's not the case. That's why I have to remove the 2 from package. So we do it as follows. We put e to the power 2 in here times e to the power the remaining part. So it will be, if you want, equal to e2 times e to the power x over 4 minus 1 over 64 x2. Voila. Now the e to the power 2 is outside, and then we apply this formula to this part, replacing x by what's in here, and then we obtain this expression. Of course, now we will do the necessary computations in here to remove all the terms of degree greater or equal to 2, and we keep only the terms of degree less or equal to 2. Sorry, we remove the terms of degree greater strictly than 2, and we keep all the terms less or equal to 2. And then we finish with this expression for the finite expansion of the composite function, exponential square root of x plus 4. Let me now take one more example. If we want to calculate the finite expansion of sine x times exponential x to the order 3 in the neighborhood of 0, then if we want to calculate to the order 3, as I told you, we need to calculate the expansions of sine x and exponential x to the order 3. So we write here the sine x finite expansion to the order 3, and in here the finite expansion of exponential x to the order 3. Now, the remark that I want to give from this example is that when we want to do the product, then we have to multiply these two finite expansions as we learned. But we have to notice something, is that when we multiply all these terms, we have to multiply 1 by x, it's okay, it will give me x. And then 1 by x3 over 3, which is good. X times x, it's x2. X times x3 is x4. I don't need it, I will put it with the remainder. Then x2 times x, it's x3, I will keep it, I need the order 3. x2 times x3, it's x5, I will remove it, put it in the remainder. And then we have this x3 in here. Okay, this x3, it will be multiplied by x, it's x4, we don't need it. By x3, it's x9, x6, sorry, we don't need it. So technically this x3 in here, we didn't need it, because all the terms obtained by multiplying anything by x3 gave x4 and plus, so it will be placed in they will be placed in the remainder. Why it's the case? Because the expansion of sine x is starting by x. In this case, the x3 of the exponential is not useful. It will not give any term, it will have no contribution to the terms of degree less or equal than 3. So if you want to calculate the finite expansion of a product to the order n, then you need to you start by saying I will calculate each of the elements of the product to the order n. But if one of the terms or one of the elements of the product starts by a degree greater than 0, then the next element of product you will calculate its expansion to the order n minus the degree of that first element. So if you calculate the finite element of a product, which is f times g to the order n, and if f starts with an order p, which means the least order of the finite expansion of f, if it's p, then you calculate the finite expansion of g to the order n minus p. You don't need to go to n, it will not be useful. This is a remark to reduce a little bit your calculations.